Almost every home has one. Millions of people use it every single day. You place your food inside, close the door, press start. And a few minutes later, your meal is hot, no flames, no glowing heating elements, just invisible energy. But have you ever wondered, how does a microwave oven actually heat food? How can invisible waves cook an entire meal? Why does your soup become boiling hot? While the bowl sometimes stays cool, why do some foods heat unevenly? And why does putting metal inside create sparks? By the end of this video, you'll understand how microwave ovens actually work, how microwaves are generated, why water molecules heat up, why some foods cook faster than others, why metal sparks, and why microwave ovens are one of the most misunderstood engineering inventions ever created. Microwave ovens have completely changed the way we prepare food, from reheating leftovers to cooking frozen meals. They save millions of people time every single day. Today, microwave ovens can be found almost everywhere: homes, restaurants, hotels, hospitals, offices, and convenience stores. Yet despite using them so often, most people don't actually know what's happening inside. Many believe microwave ovens heat food from the inside out. Others think they make food radioactive. Some even believe standing too close is dangerous. The truth is far more interesting. Behind that small kitchen appliance is an incredible combination of electromagnetism, vacuum electronics, wave physics, materials science, and thermal energy. By the end of this video, you'll understand exactly how all of these work together to heat your food safely and efficiently. History of microwave ovens. The story of the microwave oven begins during World War II. Scientists were developing radar systems capable of detecting aircraft. One of the key components inside these radar systems was a powerful device called the magnetron. Its job was to generate high-frequency electromagnetic waves. In 1945, an American engineer named Percy Spencer made an unexpected discovery. While working near an active magnetron, he noticed that a chocolate bar in his pocket had melted. Curious about what had happened, he began experimenting. He placed popcorn kernels near the magnetron and they popped. Then he tried an egg. The pressure built up inside and the egg exploded. Spencer realized these invisible waves weren't simply warming objects. They were heating the water molecules inside them. That accidental discovery led to the invention of one of the world's most popular kitchen appliances. The first microwave ovens were enormous. They were expensive, heavy, and mainly used in commercial kitchens. But over the following decades, they became smaller, cheaper, and more efficient, and eventually found their way into millions of homes around the world. High-level overview. What a microwave oven really does. At its core, a microwave oven does one thing. It transfers energy into food. That's it. Unlike a conventional oven, a microwave doesn't use flames, it doesn't heat the air inside the oven, and it doesn't rely on hot metal surfaces to cook your food. Instead, it uses a special type of electromagnetic wave called a microwave. These waves travel into the food where they interact with certain molecules. As those molecules move faster, they generate heat. That heat then spreads throughout the food until it's ready to eat. Here's the simplified process. 1. Electrical energy powers the microwave oven. 2. A magnetron converts that energy into microwaves. 3. The microwaves are directed into the cooking chamber. 4. The waves penetrate the food. 5. Water molecules absorb the microwave energy. 6. The molecules begin vibrating rapidly. 7. That molecular motion produces heat. That's the bird's eye view. Now let's go deeper. Understanding electromagnetic waves. To understand microwave ovens, you first need to understand electromagnetic waves. Electromagnetic waves are simply a way that energy travels through space. In fact, you're surrounded by them right now. Radio stations use them to broadcast music. Wi-Fi routers use them to connect your devices to the internet. Cell towers use them to transmit phone calls. Visible light. The light that allows you to see the world is also an electromagnetic wave. The only difference between these waves is their frequency and wavelength. Scientists arrange them on something called the electromagnetic spectrum. On one end are radio waves, which have long wavelengths and low frequencies. On the other end are high-energy waves like X-rays and gamma rays. Microwaves sit somewhere in between. They have shorter wavelengths than radio waves, but much longer wavelengths than visible light. Most household microwave ovens operate at a frequency of approximately 2.45 GHz. That means the waves oscillate about 2.45 billion times every second. This frequency wasn't chosen by accident. It was selected because it's highly effective at transferring energy to water molecules, while remaining practical for cooking foods safely and efficiently. But generating these waves requires a very special device. A device that has remained the heart of microwave ovens for decades. It's called the magnetron. The magnetron. The magnetron is the heart of every microwave oven. Without it, microwave cooking simply wouldn't exist. Its job is surprisingly simple. It converts electrical energy into microwave energy. But how does it do that? Inside the magnetron is a heated metal component called the cathode. When electricity heats the cathode, it releases tiny negatively charged particles known as electrons. These electrons naturally want to move toward a positively charged outer cylinder called the anode. If that happened in a straight line, the magnetron wouldn't produce microwaves. So engineers added something clever: powerful magnets. These magnets create a magnetic field that bends the path of the electrons. Instead of traveling directly to the anode, the electrons begin moving in circular paths around the cathode. As they spiral through specially designed metal cavities, they generate powerful electromagnetic waves. Those waves are microwaves. The cavities inside the magnetron are carefully engineered so they naturally resonate at a frequency of 2.45 GHz. This allows the magnetron to generate microwaves efficiently and consistently every time you turn on the oven. Although the magnetron is only one component, it's responsible for producing all the energy that eventually heats your food. Once those microwaves are generated, they need a way to reach the cooking chamber. That's where another important component comes in: the waveguide. How microwaves enter the oven. The microwaves produced by the magnetron don't travel directly into the food. Instead, they first pass through a metal channel called the waveguide. Think of the waveguide as a tunnel designed specifically for electromagnetic waves. Its job is to direct as much microwave energy as possible from the magnetron into the cooking chamber while minimizing energy loss. Once the microwaves enter the oven, something interesting happens. They begin bouncing off the metal walls, again and again and again. This happens because the inside of a microwave oven is made almost entirely of metal. Metal reflects microwaves extremely well. Instead of escaping, the waves remain trapped inside the cooking chamber, continuously reflecting in different directions. As they bounce around, they pass through the food from multiple angles. Each pass transfers a little more energy into the food, gradually raising its temperature. If you've ever looked through the microwave door, you've probably noticed a metal mesh covering the glass. That mesh isn't there by accident. The holes are large enough for visible light to pass through, allowing you to see your food. But they're far too small for microwaves to escape. This simple piece of engineering keeps the energy safely contained inside the oven while letting you watch your meal cook. But here's where things become even more interesting. The microwaves themselves aren't actually hot. So, if they aren't carrying heat, what exactly causes the food to become hot? How food actually heats. Contrary to popular belief, microwaves don't actually heat food directly. Instead, they transfer energy to certain molecules inside the food. To understand this, we need to look at water. A water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. But unlike many other molecules, water has an uneven electrical charge. One side of the molecule carries a slight positive charge, while the other carries a slight negative charge. Scientists call this a polar molecule. This tiny detail is what makes microwave cooking possible. As microwaves pass through food, their electric field changes direction approximately 2.45 billion times every second. Each time the field changes, it pulls and twists the water molecules in a different direction. The molecules constantly try to align themselves with the changing electric field. But before they can fully turn, the field changes direction again. So they rotate back, then forward, then back again. Billions of times every second, this rapid molecular motion creates friction between neighboring molecules. That friction produces thermal energy. In other words, the food isn't being heated by the microwaves themselves. It's being heated by its own rapidly moving molecules. This process is known as dielectric heating. And although water molecules absorb most of the microwave energy, they aren't the only ones. Fats, sugars, and some other polar molecules also absorb microwave energy, though generally less efficiently than water. Once heat is generated, it begins spreading throughout the food by conduction. The hotter molecules transfer energy to the cooler ones until the temperature becomes more uniform. This is why even foods heated in a microwave still rely on ordinary heat transfer to finish cooking. Why some foods heat unevenly? Have you ever taken food out of the microwave only to discover that one side is scorching hot while another is still cold? This happens because microwaves don't spread perfectly evenly throughout the cooking chamber. As the waves bounce off the metal walls, they overlap with one another. In some locations, the waves reinforce each other, creating areas with stronger microwave energy. In other locations, they cancel each other out, creating areas with much weaker energy. These are known as hot spots and cold spots. If food remained completely still, some parts would receive far more energy than others. That's exactly why most microwave ovens include a rotating turntable. Instead of trying to move the microwaves, the oven moves the food. As the plate rotates, different parts of the meal pass through different regions of the microwave field. Over time, this helps distribute the energy more evenly. Some newer microwave ovens take a different approach. Instead of rotating the food, they use a component called a mode stirrer. A mode stirrer is a rotating metal fan located inside the microwave's waveguide. Its job is to continuously redirect the microwaves, changing the pattern of the waves inside the oven. Whether it's a turntable or a mode stirrer, the goal is exactly the same: to reduce hot spots and cook food as evenly as possible. But even with these systems, the type of food you're heating also makes a huge difference. Why some foods cook faster than others? Not all foods absorb microwave energy in the same way. Some become piping hot within minutes, while others barely seem to warm up. The main reason is water content. Remember, microwave ovens heat food by transferring energy to water molecules. So, foods that contain a lot of water generally heat much faster. For example, soups, vegetables, rice, and beverages usually warm up very quickly because they're rich in water. On the other hand, foods like bread, crackers, or pastries contain much less water. As a result, they absorb less microwave energy and often heat more slowly. But water isn't the only factor. The size and shape of the food also matter. Microwaves can only penetrate food to a limited depth, typically around 2 centimeters, depending on the type of food. This means that in thick pieces of food, most of the microwave energy is absorbed near the surface. The center is then heated gradually as heat travels inward through conduction. That's why a large baked potato can be extremely hot on the outside while remaining cool in the middle. The same thing happens with frozen meals. The outer layers begin absorbing microwave energy first, while the frozen center takes much longer to warm up. This is why many microwave meal instructions recommend: stir halfway through, or allow the food to stand for 2 minutes. Stirring redistributes the heat, while standing allows heat from the hotter regions to spread into the cooler ones. Even after the microwave has stopped, the cooking process continues. Why the plate sometimes stays cool. One of the most surprising things about microwave ovens is this. Sometimes the food is boiling hot, but the plate underneath is only slightly warm. How is that possible? The answer lies in the material itself. Remember, microwaves mainly interact with polar molecules, especially water. Materials like ceramic, glass, and certain plastics contain very few molecules that absorb microwave energy efficiently. As a result, most of the microwaves simply pass through them with very little energy being absorbed. Food, however, contains far more water, so it absorbs much more microwave energy and heats up rapidly. As the food becomes hotter, it eventually transfers some of its heat to the plate through direct contact. That's why the plate may feel warm, but usually not nearly as hot as the food sitting on it. Of course, not every container is microwave safe. Some plastics can soften or melt under high temperatures, while others may release unwanted chemicals when heated. That's why manufacturers label certain containers as microwave safe. They're specifically designed to withstand microwave cooking without breaking down. But there's one material that's almost always a bad idea to put inside a microwave: metal. Why metal sparks inside a microwave? One of the first warnings you'll find on almost every microwave oven is this: never put metal inside. But why? After all, metal doesn't contain large amounts of water, so why would it be dangerous? The answer lies in how metals interact with the electromagnetic waves. Unlike food, metals don't absorb microwaves. Instead, they reflect them. In fact, the metal walls inside the microwave are specifically designed to reflect microwave energy and keep it contained within the cooking chamber. The problem begins when you place certain metal objects inside. As microwaves strike the metal, they cause electrons on its surface to move rapidly. If the metal has sharp edges, like the tips of a fork or the crinkled surface of aluminum foil, the electric field becomes highly concentrated around those points. Eventually, the electric field becomes strong enough to pull electrons from nearby air molecules. The air begins to ionize, turning into an electrically conductive gas called plasma. Once that happens, electricity jumps through the air in the form of bright sparks. This phenomenon is known as electrical arcing. These sparks can damage the inside of the microwave, burn the waveguide cover, or even start a fire if flammable materials are nearby. However, not all metal behaves the same way. Some modern microwave ovens are specifically designed to work with certain metal racks or trays. These accessories have carefully engineered shapes that distribute the electric field safely, preventing dangerous arcing. So the problem isn't simply that something is made of metal. It's the shape, size, and how that metal interacts with the microwave field. Safety systems inside a microwave. Microwave ovens are designed with multiple safety systems to ensure that the microwave energy remains safely contained. One of the most important is the door interlock system. Inside the microwave door are several safety switches. The moment you open the door, these switches immediately disconnect power to the magnetron. This stops the production of microwaves almost instantly. Even if the timer is still running, the oven cannot generate microwaves with the door open. Another important safety feature is the metal mesh built into the door window. At first glance, it looks like ordinary glass. But behind that glass is a fine metal screen filled with tiny holes. These holes are large enough for visible light to pass through, allowing you to watch your food while it cooks. But they're much smaller than the wavelength of microwaves. As a result, the microwaves are reflected back into the oven, while light passes through almost unaffected. The cooking chamber itself also acts as a Faraday cage. Its metal walls trap the microwaves inside, preventing them from escaping into your kitchen. Thanks to these engineering features, a properly functioning microwave oven can safely contain extremely high-energy electromagnetic waves while allowing you to stand just a few centimeters away. It's a remarkable example of engineering solving a potentially dangerous problem with elegant design. Common misconceptions. Despite being one of the most common kitchen appliances, microwave ovens are still surrounded by misconceptions. Let's clear up some of the biggest ones. Myth 1. Microwave ovens make food radioactive. This is false. Microwaves are a form of non-ionizing electromagnetic radiation. They carry enough energy to make certain molecules move, but nowhere near enough energy to change the atomic structure of food or make it radioactive. The moment the microwave stops operating, the microwaves disappear. Nothing remains inside the food. Myth 2. Microwaves cook food from the inside out? Not exactly. Microwaves only penetrate food to a limited depth. Most of the energy is absorbed within the outer few centimeters. The center of thick foods is usually heated by conduction, where heat travels inward from the hotter outer layers. This is why large meals often need extra cooking time or occasional stirring. Microwave ovens destroy all the nutrients in food. This is another common misconception. In reality, all cooking methods reduce certain nutrients to some extent. Boiling, frying, baking, and grilling all cause nutrient loss. Because microwave ovens often cook food more quickly and use very little water, they can actually preserve more vitamins than some traditional cooking methods. Myth 4. Standing close to a microwave is dangerous. Under normal operating conditions, this isn't true. Modern microwave ovens are built with multiple safety systems that prevent significant microwave leakage. As long as the oven is in good condition and the door seals properly, the microwave energy remains safely contained inside the cooking chamber. Myth 5. Empty microwaves are harmless. Actually, running a microwave while it's empty is a bad idea. Normally, food absorbs most of the microwave energy. Without food inside, that energy has nowhere to go. It reflects repeatedly around the cooking chamber, and some of it can be reflected back into the magnetron. Over time, this can damage the very component responsible for generating the microwaves. Understanding how microwave ovens actually work makes it much easier to separate scientific fact from popular myth. Real-world applications. Microwave heating isn't limited to the kitchen. The same engineering principles are used in many industries around the world. In the food industry, large industrial microwave systems rapidly heat, dry, and process food products. In hospitals, specialized microwave equipment is sometimes used to sterilize medical instruments and laboratory materials. Scientists also use microwave energy in chemical research, where it can speed up certain reactions compared to conventional heating methods. Manufacturing industries use microwave heating to cure plastics, dry ceramics, and process composite materials. Even telecommunications rely on microwave technology. Although communication systems use much lower power levels than microwave ovens, they operate using the same region of the electromagnetic spectrum to transmit information over long distances. From cooking dinner to scientific research, microwave technology has become an essential part of modern life. Future of microwave technology. Like many modern appliances, microwave ovens are becoming smarter. Today's high-end models already use humidity sensors, temperature sensors, and automatic cooking programs to determine exactly how long food should be heated. Instead of relying entirely on a timer, these systems monitor the cooking process in real time and adjust power levels automatically. Some smart microwaves can even recognize the type of food you've placed inside. By combining sensors with artificial intelligence, future microwave ovens may be able to identify a meal, estimate its weight, detect its temperature, and cook it without requiring any manual settings. Engineers are also working on more efficient microwave systems that distribute energy more evenly, reducing hot spots and improving cooking performance. Research is even being carried out on solid-state microwave technology. Unlike traditional magnetrons, solid-state systems use semiconductor electronics to generate microwaves. This allows for much more precise control over the frequency, power, and direction of the microwave energy. Although they're currently more expensive, solid-state microwave ovens could eventually replace conventional designs, offering faster, more even, and more energy-efficient cooking. The microwave oven has come a long way since Percy Spencer accidentally melted a chocolate bar, and its evolution is far from over. So now you understand how microwave ovens heat food. Electricity powers a device called the magnetron. The magnetron converts electrical energy into microwaves. Those microwaves are guided into the cooking chamber where they're reflected by the metal walls. As they pass through food, they interact primarily with water molecules. Those molecules rapidly rotate back and forth, generating heat through molecular motion. That heat then spreads throughout the food, cooking it from the outside of the penetration depth toward the center. It's a remarkable combination of physics, electromagnetism, materials engineering, and thermal science. What seems like an ordinary kitchen appliance is actually a carefully engineered system designed to convert invisible electromagnetic waves into one of the things we use every day. The next time you press start on a microwave oven, you'll know there's far more happening inside than meets the eye. If there's another piece of everyday technology you'd like us to explain, let us know in the comments. And if you enjoyed this video, don't forget to subscribe to Circuits and Crank for more deep dives into the engineering behind the machines that power our world.